So far in this course, we've been looking at functions, properties of functions, graphs of functions. At the end of our last class period, we talked about a library of functions, or we started to talk about those and which functions that you needed to be familiar with and the shape of them and the properties of them. So again, the objectives for this section is to graph the functions listed in the library of functions and to be able to analyze piece-defined functions, which I call piecewise defined or piecewise functions. So in front of you is the library of functions. Again, we covered a lot of these at the end of last class period, so I'm not going to go too much into detail. But we have our constant function, f of x is equal to b, where b is some real number. Recall, we know that if we have f of x is equal to b, that's another way to write that is y is equal to b. So for any value of x, our y value is b. Our domain here, there's no trouble spots, is from negative infinity to infinity. But our range, the only y value that we're getting back is the one value of y, which is b. In this graph, everything, the function is constant everywhere. So we would say it's constant between negative infinity and infinity. The next function was our identity function. Our identity function is in the form of f of x equals x, or another way to write this is y is equal to x. So recall that if we are looking at a point like this point 1, 1, when x is 1, we could write this like this, f of 1, our y value is 1. Points can be written in the form xy or x f of x, where f of x is the y value depending on what x value that you chose. In this equation, look at the domain. There's no trouble spots. Our domain in here are all real numbers, so negative infinity to infinity, and our range, we're getting all the outputs back. We're looking at our y values that we're hitting, and we're hitting all the y values coming up from negative infinity all the way to positive infinity. So there's values here that are hitting all these y values. And so range again is negative infinity to positive infinity. We have our square function, f of x is equal to x squared. Looking at this, the domain, there's no trouble spots. In our equation and looking at the picture, the domain, we're hitting all x values, negative infinity to infinity, and our range here, the smallest y value that we're hitting is when y is 0, and then we're hitting all the y values above this. We're not hitting any y values below y equals 0. And so for our range in this case, we're going from 0 including, so in interval notation, we have a bracket 0, comma, and then infinity. Another way to state this, we could say y is greater than or equal to 0. You should be able to look at these and tell where your graph is increasing and decreasing. So if we're looking at the square root function in front of us, looking at this, we're always moving left to right. And if I'm moving left to right, notice that we're going down until we hit 0. And so we're decreasing. From negative infinity to 0. Increasing. So where we're moving up from left to right, we're using the x values here. The x values, we're starting at 0 and going to infinity. So your textbook normally uses the value here, so it would include the 0. There's other textbooks that won't include the 0 in that place where it starts or ends increasing or decreasing. So just see what they want when you're looking at the homework. On an exam, I don't think I would mark you down. I would not mark you down either way in those notations for increasing and decreasing, unless it was a starting point where, for instance, maybe this point here, it wasn't going on from negative infinity to infinity for our domain. Maybe our domain started at -3 to infinity for this identity function. And then when I put in where it was increasing, I would put in that it included the -3. But other than that, I'm okay with you doing it either way. Just see in what class, how is that textbook or your instructor wanting it. So we talked about the other functions. We still talked about these at the end of last class period. We have the cube function, f of x equals x cubed. Notice the following function here. Our domain is all real numbers and our range is all real numbers. This is strictly increasing everywhere. There's one other condition on here, and I guess there's some other conditions on the ones above. But notice we talked about even and odd functions last class period. So it was an odd function if this was symmetrical across the origin, which notice our cube function. If I folded it along the x-axis and the y-axis, this is what would lie on top of each other. It's symmetrical across the origin, and so this is an odd function. Above, let's just look at those couple ones that we just talked about. So looking at the following, the constant function, our constant function, it's symmetrical across the y-axis. Things that were symmetrical across the y-axis were even functions. So this was an even function. My identity function, y equals x, notice that this is symmetrical across the origin. So my identity function is an odd function. The square function, this is symmetrical across the y-axis. And so this is an even function. So going back to the other ones. Our square root function, this one, we do need to limit our domain. We can't have negative numbers underneath an even powered radical, or that gives us back a non-real number, an imaginary number. And so we want all of our values of our domain to give us back a real number. And so our domain for this piece, by looking at the function, I would have to have x is greater than or equal to 0. So I'm going from 0 to infinity. But I can also see it by just looking at the graph. My x value, I'm starting at 0, and then I'm hitting all the x values as I'm going to infinity. My range, those are the y values that I'm hitting. The smallest y value that I'm hitting is 0, and I'm going to infinity. This is strictly increasing. And if it asked on the interval, where is it increasing? We would say it's starting at 0 and going to infinity. This function is neither even or odd. It's not symmetrical across the x-axis or the y-axis. Our cubed root function, which was one I think we missed last time, looks similar to our graph over here. Our domain, because it's an odd index of our radical, we don't have to worry about having negatives underneath the radical. And so for our domain, we're hitting all of our x values. And so our domain and interval notation would be negative infinity to infinity. We're hitting all these x values. And our range, even though it's growing slower, it's going down. Our range is hitting all of our y values. This one, it's also strictly increasing. It's going up from left to right. And it's strictly increasing on our domain, which was negative infinity to infinity. This is symmetrical across the y-axis and the x-axis. So this one here is an odd function. Our reciprocal function is in the form of f of x equals 1 over x. We have a graph to the right of that. This one, when we're looking at the domain, we do have a trouble spot. If we have a variable in our denominator, we have to worry about the value which sets the denominator equals 0. And so in this case, we have x cannot be 0. And so we're hitting all the values from negative infinity all the way up to 0, but not including. So we put a parentheses. Union starting close to 0 on the right, but not including to infinity. Our range, we're hitting all the y values coming up from negative infinity until we get really, really close to 0, but we're never going to get there. And then we're going to hit all the y values bigger than 0. So everything but not 0. And so our range is actually the same thing as our domain above, except it's y values instead of x values. So negative infinity to 0 and then 0 to infinity. When we're starting, this is decreasing, going down left to right on the third quadrant. In the first quadrant, it's also going down left to right. So this is decreasing function, and it's decreasing from negative infinity up to getting close to 0, but not including 0, so parentheses, and then 0 to infinity. Looking at this, it is symmetrical with that origin. I can fold my paper along the x-axis and y-axis, and I get a mirror image. So this graph here, this is a odd function. The last one that we talked about in the class period last time was f of x is equal to the absolute value of x. If we look at this, we can plug any value in for x and not have a problem. And so our domain on this case was negative infinity to infinity. Our range, notice that the smallest y value that we're hitting is 0, and we're hitting all the y values above. And so our range in here, we include 0. So bracket 0 to infinity. This graph is increasing and decreasing. If I'm moving left to right, I'm going down left to right. And so it's decreasing on the interval from negative infinity to 0. And then it's increasing, we're moving up left to right. From 0 to infinity. If I folded my paper along this y-axis, I would have a mirror image. And so that tells me that this is an even function. So the next function was what we did not get to. So the rest of this video will be new material that we didn't cover in the last class period. So last function that you should be familiar with, not as much so as the other ones, but this is called the greatest integer function. And there's different ways to denote it. Your book denotes it with this f of x or y is equal to int x. And this means that if we're plugging a value in for x, our output has to be the greatest integer less than or equal to x. Okay, so recall your integer set of integers. They're all your real numbers. Dot, 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 coming in from negative infinity and looking like the form -2, -1, 0, 1, 2, dot, 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 going on to infinity. So the integers are these numbers. And so let's just look at the graph really quickly. So let's actually look at positive numbers because those are the easier ones to look at, and then we can talk about the negative. So if I chose a number between 0 and 1. So for instance, let's just say I chose 0. Well, 0 is an integer. So my output is going to equal x because it's an integer. And so you can see here when x is 0, y is 0. And so we have a point at 0, 0. But if I chose a number anywhere in between this 0 and 1, not including, for instance, 1/4, well, 1/4 is not an integer, but the output has to be the greatest integer less than this number, 1/4. Well, 1/4 falls between 0 and 1, and the greatest integer less than 1/4 would be 0. And so this is why we get back 0 for this piece. So any number you chose between 0 and 1, but not including 1, you would have a y value of 0. But once I hit that number 1, 1 is an integer. And so it's one that's equal to, because it's an integer, I'm going to have 1. And so that's why we have a solid circle here. But if I hit something in between 1 and 2, not including 2, so for instance, 1.5, 1.5 is not an integer. 1.5 falls between 1 and 2, and the greatest integer less than 1.5 would be 1. So I hit the number 1.5, 1 on the graph. So I'm hitting all the values right in here between 1 and 2 are going to give me back 1 except for 2. Because 2 is an integer, it's going to give me back 2. So all numbers in between 2 and not including 3. Well, anything bigger than 2 and less than 3 is not an integer, but the greatest integer less than would be 2. So we have this step function in here. If we're looking at negative numbers, well, -2, we would get back -2. I'm sorry, this is -1. -1 is an integer, we would get back -1. And if I'm looking at -0.5, well, -0.5 is not an integer, but the greatest integer less than negative 0.5 is -1. And so that's why we're getting the points in here. Anything between -2 and -1 would give us the greatest integer of -2. You may see if you're looking this up or reading other textbooks, there's other notation that could be used. This is what I've seen in the past and have used in the past, is this bracket kind of, or a double bracket kind of around the X. So you might see our bolded bracket. So this would also represent the greatest integer function. I haven't heard it called this, but it's also called the floor function, where your bracket is actually kind of look like an L, but it doesn't have that piece on the top. So if we're looking at this, notice it's never increasing, it's never decreasing. It's always constant. And we would say that it's constant. We would look at each piece of these intervals and take the union of them. If I was looking at my domain, I can put any number in there and I'll get back an output. So it's negative infinity to infinity. But my range, notice I'm never hitting any number that's not an integer. So my range, maybe a way I can say this is y. That's the set builder notation. So a curly bracket y, vertical line such that y, kind of funky E, means contained. It's an integer. So this funky Z in mathematics is just a symbol for integers. So next thing that we're going to look at are what are called piecewise functions. So we have this piecewise function in front of us. What it means is that we have different equations for our function, and the different equations, there's different domains related to those equations. For instance, in this problem in front of us, we have f of x is equal to 2/3 times x plus 1 if x is less than 1. And we have negative 2x plus 1 if x is greater than or equal to 1. So looking at this, let's look at part A. It says find f of 0. Well, f of 0, it's telling me that we want to know what is y when x equals 0. So you need to go in and see which equation to use. So when x is equal to 0, you look at your inequalities, and is 0 less than 1? Yeah, 0 is less than 1. So this tells me that I'm going to use equation 1. So we're going to go into equation 1, and wherever we see an x, we're going to replace that with 0 to get our output. So we have 2/3 parentheses, plug in 0 plus 1. So simplifying, 2/3 times 0 is 0, and then 0 plus 1 is 1. So a couple ways to write this. 0 f of 0, which doesn't tell us too much because we don't know what f of 0 is unless we look at it or to figure out what it is. Or that's the point 0, 1. So that's a point on the graph of our piecewise function. The next part for part A says let's find f of 1. So here we're looking at when x is equal to 1. So 1 is not strictly less than 1, so I'm not going to use that first equation. But 1 is greater than or equal to 1. So 1 is defined and using the second equation. So I'm going to use equation 2. So equation 2 has -2. I see an x there, put parentheses, plus 1. Now let's drop in 1 inside the parentheses and simplify. So we get here, this is -2 plus 1, which is -1. So when x is 1, my y value I get back is also 1. And then evaluate f of 2. So you're going to look at when x equals 2, which inequality that satisfies. So 2 is not less than 1, but 2 is greater than or equal to 1. So again, in this value, I'm going to use equation 2. So we have -2 parentheses. So I see an x plus 1. Drop in 2 inside the parentheses and simplify. We get -2 times 2 is 4, or -4, plus 1. So -4 plus 1 gives us back -3. So in this case, we have a point when x is 2, y is -3. So if you're evaluating a number on a piecewise function, you need to determine which equation you're going to use. What value of the inequality does that number you're plugging in satisfy? And that should tell you which equation you're going to use there. When it's asking us to find the domain of a piecewise function, look at your stipulations, your inequalities. These are telling you which x's you're using. And so if I look at this domain, I'm looking at x is less than 1, or we're looking at x is greater than or equal to 1. Well, x is less than 1, that's hitting all the values -infinity to 1, not including. Union, well, if I'm hitting x is greater than or equal to 1, I am hitting 1 to infinity. So technically my domain is this -infinity to infinity. So that's part B. Part C, let's locate any intercepts. The point back here, when x was 1, we got back y was -1. This should be a -1 right here. I dropped my negative when I wrote it. Okay, so let's look at the intercepts. So we have x-intercepts and we have y-intercepts. Our x-intercept is going to be the harder one to find, but the y-intercept, we know what x is. We know x is 0. So part C. So if I'm looking at the y-intercept, this is when x equals 0. So I'm going to go up here and I'm going to determine which equation I'm going to use. So when x is 0, 0 is less than 1. So that tells me that I need to use my first equation. And so I can write this as f of 0 tells me to use equation 1. So I have 2/3, we already did this work above, times 0 plus 1, which gave us back 1. So we have a y-intercept at the point 0, 1. So the x-intercept is a little harder. The x-intercept is when y is equal to 0, or another way to say that is when f of x is equal to 0. So we're trying to figure out what x gives us back y equals 0. It could be any equation in that piecewise function. And so we have to look at all the equations in our piecewise functions and set those equal to 0 to see if there is any x-intercept that falls in the domain of that equation. Okay, so for our x-intercept, we're going to let y equal 0, or another way to say it is f of x equal to 0, and solve for x in each equation. So I'm looking at when is the first equation 2/3 x plus 1, when is this equal to 0? So I want to isolate x. I can do so by subtracting 1 on both sides of my equation. And I would get 2/3 x is equal to -1. I want to get rid of the 2/3 in front of my x. It's multiplication. I can undo that by division, but I don't want to deal with a fraction divided by a fraction. So I can bypass that by multiplying by the reciprocal to make that a 1 in front of the x. So let's multiply both sides of our equation by 3/2. Doing so, I get x is equal to -1 times 3/2 is -3/2. This was for equation 1. So let's look for equation 1. We need to see, is our value of x that we've got work for this inequality? So since -3/2 is less than 1, this is going to be an x-intercept. X equals -3/2 is an x-intercept. It's possible that there's another x-intercept because we have another equation here for our function f of x. And so again, we want to look at when is that equation, -2x plus 1, when is this one equal to 0? So if I solve for this and I have an x value that falls in this inequality of 1 or bigger, then it's going to be an x-intercept of our function. If not, if it falls in the other inequality, then it's not. So solving for x here, I would subtract 1 on both sides of my equation. And so I get -2x equals -1. And then I would divide both sides by -2. -1 divided by -2 gives me back +1/2. But x equals 1/2. This is not greater than or equal to 1. So this actually is not an x-intercept. So the only x-intercept that we have occurs when we have -3/2. X is 0, or at that point. So the last piece we want to do is we want to graph this piecewise function. And so when we're graphing piecewise functions, we want to graph each equation. But when we choose our values for x, we want to make sure that it's falling inside of this inequality. except when it's the n value of an inequality. So for instance, for this first equation, 1 is an n value of this inequality, even though it's not included. I do want to see what's happening when x equals 1 here. I would just put that it's an open circle when I am plotting the points. So let me give us some room so that we can go through and graph this piecewise function. Okay, so let's plot some points for our first equation. So again, we want to see what's happening at the end bound of our inequality. So I want to see what's happening to this equation when x is 1. So if I go back into this equation and I plug in 1 wherever I see an x, I would get 2/3 all times 1 plus 1. So simplifying, I get 2/3 plus 1. In order to combine those, I need to rewrite 1 with a common denominator. So I'm going to write that 1 as 3/3. So this would give me back 5/3. I'm going to put a little note to myself that this is an open circle because this is actually not included. But as we get closer and closer to 1 on the left-hand side, then we are going to get closer and closer to the y value 5/3, but not getting there. So now let's choose something which is less than 1. So if we plug in 0, wherever we see an x, because 0 is less than 1, we get back 0 plus 1, which is 1. So we can choose what numbers we want to choose. And so I would choose something that was divisible by my denominator so I don't have to deal with fractions. So what about x equals -3? So if I looked at f of -3, plugging that in wherever I saw an x, I would have 2/3 parentheses plus 1, plugging in -3. Well, 3 in my denominator cancels into or goes into -3, -1 times. And so we're left here with 2 times -1 is -2 plus 1, which gives us back -1. So at -3, we have a y value of -1. So I'm thinking that that's probably enough to go in and just graph that piece of our piecewise function. So when x was 1, we had a y value of 5/3, which is 1 2/3, or it's 1.67. So just approximate it. And it was an open circle. At 0, we had 1. And at -3, we have -1. So this right here is a line. It's in the form y equals mx plus b. We're going to have a graph of that line that is going to have the domain. Let me move it up maybe a little more. Where x is less than 1. So do not extend that line where x is bigger than 1, because that would not be part of our domain for that piece. And so now we've graphed the first equation. We want to go and we want to graph the second equation. So again, we can plot points. We always want to see what's happening at an inbound of the inequality. So 1 is also an inbound of this inequality. So if we go in here and we plug in 1, wherever we see an x, in the second equation, we have -2 parentheses, so times 1 plus 1. So here we have -2 plus 1, which was -1. So 1, -1 is a point. And this is a closed circle because it's equal to, x is equal to 1 for that equation. So we have a point here at 1, -1, and it's a closed circle. So just choose a couple numbers that are bigger than 1. So for instance, 2. If we go back into our equation and wherever we see an x, we plug in 2, we would get back -2, parentheses, and times 2 plus 1. So here we get -4 plus 1, which gives us back -3. So we have a point at -2, -3. So when x is 2, we have -3. So this piece of the function is decreasing. It's starting when x is 1, including 1, and then it's going to go down. I'm not going to extend that piece to the left of 1 because it's not part of the domain for that equation. So there is the graph of our piecewise function. The last part of that question, excuse me. The last part of that question wanted to know the range. Looking at piecewise functions, and usually it's helpful to see the graph of it to tell what the range is. And so notice that my range here, that blue piece of the graph, it's hitting all the values from -infinity all the way up to y equals -1. Our pink value of that graph, so it's hitting all these numbers. It's hitting all the y values from -infinity all the way up to, but not including, this 5/3. So all of the y values that we're getting are coming from -infinity all the way up to 5/3, but not including 5/3, so we have a parentheses. Another way to state this is y is less than 5/3. These are typical questions you would see on an exam. So let me go a little bit further for you. I would probably go a little further and ask you, where is this function increasing and where is it decreasing? And where is it constant? So moving left to right, where are we going up? And you're using the x values. So we're going up from -infinity until we hit the x value, but not including 1. This is where it increases. So -infinity, parentheses 1. Or another way to state this is x is less than 1. Where is it decreasing? So looking left to right, it's going down. Graph is going down, starting at 1. I would actually include it because of that bracket, because it's a solid circle. to positive infinity. So this is where it decreases. So using the x values, starting at 1, going to infinity. Another way to state this is our x value is greater than or equal to 1. So let's look at one more example where we have a piecewise function and we have to answer questions about this piecewise function. So we're given f of x. The first equation is x plus 2. And this occurs if x is between -4 and including -4 to x equals 2. So -4 is less than or equal to x, which is less than 2. We get the f of x is equal to 2 if x is just equal to 2. And we're going to use the equation x squared over 3 if x is bigger than 2. So when it's asking us to find f of 0, look at where 0 is located. Well, 0 falls between -4 and 2. So that tells me that I'm going to use the first equation when I evaluate x equals 0. So I'm going to go in here, plug in 0 into the first equation wherever I see an x. And doing so, f of 0, I get back 2. So we have a point at 0, 2. I'm going to have to graph this. I might as well put this in here. If I'm looking at f of 2, well, when x is equal to 2, my y value is 2. So when x is equal to 2, I have a y value of 2. And then we have f of x equals 3. Well, x equals 3. That's a value of x. 3 is greater than 2. So that would tell me that I would use my third equation. So if I plug in 2 wherever I saw an x, I'd have 2 squared, which is 4. 4 divided by 3. My domain, I need to be careful here. Because of the first inequality, I'm not hitting all the values from negative infinity to positive infinity. So I'm hitting from -4, including 4, to 2. But then I get 2 here. And then I hit all the numbers which are bigger than 2. So my domain, a couple ways I can write this. I'm starting at -4, including my x value. So bracket -4. And then I'm going to infinity. Or another way to state that is x is bigger than or equal to -4. Locate any intercepts. Well, the y-intercept we already found. The y-intercept occurs when x equals 0. When x equals 0, that falls inside the first equation. For a, we already found that. We have a point of 2. So y-intercept when x is 0, y is 2. We have a point at 0, 2. The x-intercept was a little harder. That's where we had to set each equation equal to 0 and solve for x, and then determine does that value of x fall in the inequality for that equation. If it does, then it's part of our x-intercept. If that value of x, which sets the equation equal to 0, does not fall in that inequality or stipulation for that equation, then it's not part of the domain. I'm sorry, not domain. Well, it's not part of the domain for that equation, so it's not an intercept. So looking at x-intercepts, We're going to set each equation equal to 0 and solve for x. So looking at my first equation, x plus 2, set that equal to 0, solve for x, and I get x is negative 2. If negative 2 falls in between negative 4 and 2, which it does, then it is an x-intercept. And so we have an x-intercept when x is negative 2, y is 0. So I actually know that that's a point on my first equation. X is negative 2, y is 0. Let's look at the second equation, 2. When is 2 equal to 0? Well, 2 is never equal to 0, so we don't have any x-intercept at that piece. And then the last piece I need to look at, our third equation I need to look at, is when is x squared over 3 equal to 0? Well, we can clear our equation, or not clear our equation, we can clear our denominator or fraction by multiplying both sides by our common denominator, which is 3. So we get x squared here is equal to 0 times 3, which is 0. Take the square root of both sides, plus or minus the square root is 0. The number you can square to get 0 is 0. So this would be when x is 0. And I'm using the third equation, and 0 is not larger than 2. So this is not an x-intercept on my graph. So you have an x-intercept at negative 2, 0, and we have a y-intercept at 0, 2. So now we want to graph this equation. Let's graph the first equation. X plus 2. So we saw that we already have some points for that first equation. When x was 0, y is 2. At negative 2, we had 0. We want to know what's going on the inbounds of these inequalities. So we want to know what's happening when x is negative 4. So if we plug in negative 4 into x plus 2, we get negative 4 plus 2 is negative 2. This is a closed circle because it has the equal to the inequality. So I have a point at negative 4, negative 2. And then I want to see what's happening at positive 2 for the first equation, even though it's not included there. But it's an end value of my inequality, and so I want to plug it in and see what I get back for x. Actually, I want to plug in positive 2. I already did negative 2. Positive 2 is the end value. So 2 plus 2 gives me back 4. And this is an open circle. Okay, so we don't want to go past x equals negative 4 or x equals 2. And so we're just going to have a line segment here with no arrows joining those points. So that is the graph of the first equation. The second equation is just saying when x is 2, what is y? Y is also 2. So I have a solid circle
at 2, 2. Doesn't go to the left or the right of that point for that equation. And then the last equation is for values of x which are bigger than 3. Sorry, not bigger than 3. I'm looking at the denominator, bigger than 2. So we saw at 2, we got 4/3. This is a closed circle because it's included there. So 4/3 is 1 1/3 or 1.33. So at 2 actually is not closed. It's greater than, it's open. So at 2 4/3, we have an open circle. And then let's choose numbers to plug in for x that are bigger than 2 into this equation. I want something divisible by 3. So what about plugging in 3, just so I don't have to deal with a fraction? So if I plug in 3, I get 3 squared, which is 9, all divided by 3, which is 3. So I have a point here at 3, 3. That's probably good enough. It's a line, it's linear. So I'm going to start here at 2, 1. I'm sorry, 2, 1. It's 2 4/3. I'm not going to extend it to the left of 2 on this graph. And then it's going to, x is going to infinity here. So I can put an arrow. Oops. So we have a picture of our graph. Now looking at it, it wants the range. So looking at the range, I would look at my smallest y value. My smallest y value occurs when x is, or not x, it occurs when y is -2. So that should be here. Not quite to scale. We'll make it. Okay, so we have our y value starting at -2 is the smallest y value, but we're hitting all the y values for the first piece all the way up to and not including 4. But this third equation hits the y values bigger than 4 and including 4. So our range, we're hitting all the values from y equals -2 to y equals infinity. So you should also be able to tell me where the graph is increasing. So it's increasing from -4 to 2, and then it's increasing from 2 to infinity.
So our next example, we're actually given the graph and we want to come up with a piecewise defined function that defines this graph. I noticed that we have 2 pieces of our graph, or there's 2 different pieces of this graph. And so if I'm looking at this first piece in here, we can see that those are for values of x. If x, it was a solid circle on both the endpoints. So it's including -1. So if we have -1 is less than or equal to x, is less than or equal to, and it's including the x value of 0. I see that this is a line. And so we can think of things in the form of y equals mx plus b. Let's look at what our slope is. So from this point, -1, -1, we're rising 1, and then we're running over 1. And so I see my slope is 1 there. So I have 1 times x. My y-intercept here is 0. So this is just the equation x, y equals x. If I look at the second piece in here, this is when x is bigger than 0, but including x equals 2. So 0 is less than x is less than or equal to 2. This is a constant. So my y value in here is always 1. And so my equation here, f of x is equal to 1 for the second equation between 0 and 2, including 2. And so we've set up our piecewise equation that satisfies this graph. So we have an example here of parking at O'Hare International Airport. The short term, no more than 24 hours, parking fee, capital F, in dollars, for parking X hours on a weekday at O'Hare's International Airport main parking garage can be modeled by the function. So the first equation is 2 minus 3, the greatest integer function of 1 minus x. If x is between but not including 0 and 2, 4. So these x is hours. So that's how much you're going to pay if you go inside the garage and stay there less than or equal to 4 hours. If you are in the garage and you park more than 4 hours, but less than or equal to 9 hours, then you're going to pay 2 minus 9, greatest integer function of 3 minus x. And then if you park in the garage for more than 9 hours, but less than or equal to 24 hours, you're going to have a flat rate of $74. So the following wants us to determine the fee in the short-term parking garage for 2 hours. So you're going to look at which equation you're going to use. X is 2, so which inequality does 2 fall into? 2 is between 0 and 4. And so for f of 2, we're going to use equation 1. So we have 2 minus 3, greatest integer function of 1 minus, we're going to replace x with 2. So this is equal to 2 minus 3 times, well, the greatest integer function of -1. So this is equal to 2 minus 3. Well, the greatest integer less than or equal to -1 is -1. So we get 2, -3 times -1 gives us +3. So this is equal to 5. So if you park in the garage for 2 hours, they're going to charge you $5. Part B, we want to look at what's happening when we park in the garage for 7 hours. Well, 7 hours falls between 4 and 9. So this tells me to use the second equation. So second equation is 2 minus 9, the greatest integer function of 3 minus x. So 2 minus 9 all times the greatest integer of 3 minus 4. So we got 2 minus 9 times the greatest integer of -1. Well, the greatest integer of -1 again is -1. We're going to be multiplying that by the -9 in front and summing it to the 2. So we have 2 plus 9, which gives us 11. So parking in the garage, I don't know why I put 4 there. It should have been 7. Just go back and change that. If it was 4 hours, I would have used the first equation. And then the greatest integer of 3 minus 7. So that would be the greatest integer of -4. Well, -4 is an integer, so the greatest integer is -4. So we have 2. -9 times -4 is plus 36. And this is 38. So parking in the garage for 7 hours, you're going to pay $38. For 15 hours, that falls between 9 and 24. So f of 15, we're using the third equation. There's no x in there. So when I plug in 15 there, I still get back 74. So if we park in the garage for 15 hours, we're paying a rate of $74. Part D, 8 hours and 24 minutes. Well, 8 hours and 24 minutes. That falls in between the second equation. Inequality. It's between 4 and 9. So we're going to look at f of. So we could change our 24 minutes. Let's change that to hours. Well, I want this in terms of hours. So I'm going to multiply it by following. I know there's 60 minutes is the same thing as 1 hour. So if I look at 24 divided by 60 is 0.4. So this is 0.4 hours. So I know that 8 hours, 24 minutes in terms of just hours is 8.4. So I have 8.4, plugging it into the second equation. We have 2 minus 9 times the integer function of 8.4. So this is equal to, and then I forgot that I needed to, it's 3 minus 8.4. So we have 2 minus 9 times the integer function. Well, 3 minus 8.4, that is going to give me negative 5.4. So the greatest integer
that is less than -5.4, that's an integer, is -6. So we're going to have here 2 minus 9 times -6. Well, 9 times 6 is 54, so we have 2 plus 54, which gives us 56. So parking for 8 hours and 24 minutes, you would pay $56 for parking in the garage. So this was the rest of our textbook 3.4.